Alright everyone, today we're diving deep into what I like to call the hidden art of hydropower magic. Specifically, the fascinating world of asterisk inverted D-shaped tunnel design and its application in hydropower projects. Now, when we think about hydropower, we often envision these mighty dams and large reservoirs. But the real work, the intricate engineering that makes it all possible, often happens underground, where the tunnels extend like veins through the earth. Fascinating, right?
Wow, yeah, that is super interesting. I always imagined hydropower as this straightforward thing, like dam, water, electricity, but there's a whole times tunnel world going on underneath. What exactly makes this inverted D-shaped design stand out from, like, regular tunnel designs?
Great question. The inverted D shape is unique because it beautifully balances structural stability with functional usability. You see, in places with high overburden, where there's a lot of material above the tunnel, this shape is particularly well suited. It can handle the pressure and offers enough space for maintenance, drainage, and inspections. Think of it like designing a tunnel to handle a pile of books on top of it, while still ensuring you can pull one book out if you need to, right?
I love that analogy. So it's like when you're trying to pull out a single book from a stack of 100, but you have to be careful not to topple the entire stack. Does this design help with the flow too, like, the water moving through the tunnel?
Absolutely. The design also incorporates hydraulic considerations, which means it factors in how much water is being discharged, the velocity of flow, and the slope of the tunnel. This ensures that water can move efficiently from the intake to the surge shafts without any bottlenecks. Picture water flowing down a smooth slide. It needs the right angles and curves to zip down quickly without getting stuck.
A water slide. Haha, that makes it really clear. Okay, so how do they actually dig these tunnels? I've heard of different methods, but what's the process like for these inverted D-shaped tunnels?
Excellent point. They typically use the drill and blast method, so the first step involves marking the area and drilling holes into the rock. These holes can range from 1.5 to 3.5 meters deep. They're drilled in specific patterns and typically have diameters of about 32 to 45 millimeters. It's like preparing for a big bake sale, where you don't just toss everything into the oven, you measure, plan, and execute it perfectly.
That's a really cool comparison. So it's pretty precise, huh? But is it like those action movie explosions, or is it more controlled? Laughs.
Haha. Well, it's definitely more controlled. After drilling, the next step is charging those holes with explosives, which are sequenced to minimize overbreak. That's when the rock breaks more than intended, and vibrations. It's all about finesse, rather than a full-on explosive scene from a blockbuster.
I see. And once they blast it, what's next? Do they just walk in, or is there more to it?
Great question. After the blast, they go through a process called mucking and ventilation. This involves loading and transporting the blasted rock, known as muck, while temporary ventilation systems are set up to remove harmful gases. So they're not just walking into a dusty, dangerous cave. Safety and air quality are top priorities.
Wow, safety first. I guess it wouldn't be a good idea to have a bunch of miners passing out, right? What about after excavation? How do they support the tunnels so they don't cave in?
That brings us to the support system, often referred to as the Norwegian method, or NATM. Here, the support is adjusted in real time based on the rock's strength. They use a combination of materials like shotcrete, rock bolts, wire mesh, and steel ribs. It's kind of like putting on layers of protective gear depending on the weather. You wouldn't go out in just a t-shirt if it's snowing, would you?
Haha, definitely not. And how does this relate to keeping the tunnels functioning over time?
Great segue. After the tunnel is completed, they apply a final lining, typically with concrete or steel, ensuring smooth flow and operational efficiency. The head race tunnel transports water from the intake to the surge shafts, while the tail race does the reverse, discharging water from the powerhouse back to the river. It's a perfect circle of life for water.
Ah, W, that's so poetic. But doesn't that mean there's maintenance involved too? What's that like?
You got it! Regular inspections are an essential part of ongoing maintenance, focusing on crack detection and sediment buildup. It's like taking your car in for a regular checkup. If you neglect those little things, they could turn into much bigger problems later on.
So in a way, this whole process is like a living organism, right? You build the tunnels, maintain them, and make sure they can keep doing their job, just like taking care of a pet. I love that.
Exactly. It's all linked together. The design, excavation, support systems, and ongoing maintenance are crucial for the successful operation of hydropower projects. It's a cohesive partnership where every part plays a key role.
This has been such an eye-opener. I had no clue there was so much complexity involved. I can't wait to learn more about it.
And that's the beauty of engineering. There's always more beneath the surface, quite literally.
That makes sense. It's like peeling an onion. There's layer after layer to uncover.
Exactly. Just when you think you've seen it all, there's still so much more to discover.
I'm so excited about learning all of this. I feel like I just scratched the surface.